There is one force that holds galaxies together, keeps your feet on the ground, and bends the very fabric of space and time, and Richard Feynman, one of the greatest physicists who ever lived, openly admitted he could not explain it. That force is gravity, and before you think this is about complicated maths or abstract theory, let me be clear, Feynman wasn't saying he couldn't calculate gravity. He could do that brilliantly. What he confessed was far more unsettling. He could not tell you why gravity exists at all. In his famous Feynman lectures on physics from the 1960s, and in various recorded interviews, he kept returning to a theme. We can describe how gravity behaves with extraordinary precision, but if you ask why masses attract each other across empty space, physics gives you silence. Absolute silence. Now, most of us are taught that Newton discovered gravity, but here's what your textbook probably glossed right over. Newton himself was deeply troubled by his own theory. He gave us the equations. He refused to explain the mechanism. He thought the mechanism was, frankly, absurd. Newton wrote that the idea of one body acting upon another across a vacuum, without anything connecting them, was so great an absurdity that no person with a competent faculty of thinking could ever accept it. He gave us the most powerful gravitational equations in history and then said he had no idea how any of it actually worked. Then came Einstein. General Relativity, published in 1915, gave us a completely new picture. Gravity is not a force at all, Einstein proposed. It is the curvature of spacetime caused by mass and energy. Objects do not get pulled toward each other. They follow the natural curves in the fabric of the universe itself. This picture is extraordinarily beautiful, and it works. GPS satellites must account for relativistic time dilation caused by Earth's gravity, or they'd be off by kilometers every single day. Gravitational waves, ripples in spacetime itself, were predicted by Einstein in 1916 and detected a century later in 2015. The mathematics is breathtaking, but here is the catch. Einstein's general relativity treats spacetime as a smooth, continuous fabric, and that creates a fundamental crisis because the rest of modern physics, quantum mechanics, says that at its smallest scales, the universe is anything but smooth. It is grainy, probabilistic, and deeply, irreducibly weird. Every other fundamental force in nature has been successfully described using quantum field theory. Electromagnetism has the photon. The strong nuclear force has gluons. The weak nuclear force has W and Z bosons. Each force has a quantum carrier particle that transmits it. Gravity has no confirmed quantum carrier. None. Physicists have proposed a theoretical particle called the graviton, the hypothetical quantum of the gravitational field. We have never detected one. And the mathematics involved in building a quantum theory of gravity using the same framework as the other forces produces answers that are literally infinite. What physicists call non-renormalizable divergences, the equations simply collapse. To understand how bad this is, consider the following. Using quantum electrodynamics, physicists can calculate the magnetic moment of the electron to better than 10 decimal places of accuracy, one of the most precise predictions in all of science. Try the same kind of calculation for gravity using gravitons and the standard approach. You get infinity, not a large number. Infinity. The mathematics becomes meaningless. This is the core of what Feynman was pointing at. We can describe the effect of gravity with remarkable accuracy. We know exactly how much things fall. We know precisely how spacetime curves around a massive object. But the why, the underlying quantum mechanism, the deep physical story of what gravity actually is, remains completely beyond us. And this is not just a philosophical concern. Without a quantum theory of gravity, we cannot understand what happens inside a black hole near its singularity. We cannot understand the very first fraction of a second after the Big Bang, when the universe was so incredibly dense that quantum effects and gravity were both operating at full strength simultaneously. Two major research programs have spent decades trying to crack this. The first is string theory. In string theory, all particles, including the graviton, are actually tiny vibrating strings of energy. The mathematics is extraordinarily complex, but string theory does naturally produce a graviton without those dreaded infinities. That is genuinely impressive. The catch with string theory is that it requires extra spatial dimensions, typically 10 or 11 of them, that we have never observed and have no direct experimental evidence for. It has also not yet produced a single clearly testable, falsifiable prediction that distinguishes it from competing theories. Critics argue it is beautiful mathematics still searching for physics. The second major approach is loop quantum gravity. Rather than modifying our picture of particles, loop quantum gravity modifies the very structure of spacetime itself. It proposes that space is not continuous but made of tiny discrete loops or quanta, like pixels in a photograph, but at a scale 10 billion times smaller than the width of a single proton. Loop quantum gravity has genuine achievements. It resolves the singularity problem inside black holes by replacing infinite density with a maximum density the universe cannot exceed. It offers a model of the Big Bounce, where the universe did not begin from nothing but collapsed and rebounded from a prior state, but it still struggles to fully recover Einstein's equations at large scales. There are other proposals on the table: causal dynamical triangulations, asymptotic safety, entropic gravity, emergent gravity. Each approaches the problem from a different angle. None has yet achieved scientific consensus. The honest answer right now is straightforward. We do not have a complete, experimentally verified quantum theory of gravity. What makes all of this so extraordinary is the contrast with the rest of our knowledge. We can model the electron's magnetic moment to 10 decimal places. We've mapped the cosmic microwave background, the afterglow of the Big Bang, in stunning detail. Modern physics is almost unimaginably precise. And yet gravity, the most obvious force in daily life, is the one that defeats us. Feynman understood this paradox deeply. In his lectures and interviews, he returned to the same theme again and again. Knowing how something happens is fundamentally different from knowing why it happens. Gravity is the ultimate example. We have the most accurate description in the history of science. We lack the deepest explanation. Those are not the same thing. Some physicists now wonder whether we're even asking the right question. Perhaps gravity isn't fundamental at all. Perhaps it emerges from something deeper, from quantum entanglement, from information theory, from thermodynamic principles. Eric Verland's entropic gravity proposal suggests gravity is a statistical emergent force, much like temperature emerges from the invisible motion of countless molecules. Others argue the problem isn't gravity, it's our concept of spacetime. Perhaps spacetime itself is not fundamental, but is woven from something more basic and more quantum mechanical that we have not yet identified. The ADS/CFT correspondence from string theory and ideas from holography hint tantalizingly in this direction. Here is what we can say with full confidence. Gravity is the last of the four fundamental forces to resist quantization. General relativity and quantum mechanics are individually the most tested and verified theories in all of scientific history. And at the deepest level, they are fundamentally incompatible. That incompatibility is not a footnote. It is the unresolved heart of physics. Richard Feynman once said that science is a long history of learning how not to fool ourselves. The honest position on gravity is exactly that. We have extraordinary tools. We have extraordinary descriptions, and we know enough to know how much we still do not know. That is not a failure of physics. That is physics being completely honest with itself, and that honesty perhaps is the most Feynman thing of all.